Part 1. What is quantum spin? Quick introduction to pique your curiosity. Perhaps you've heard of Schrödinger's cat-in-a-box analogy of quantum mechanics. Perhaps you're familiar with how magnetic domains and materials align together to create ferromagnetic properties. Maybe you've learned of Hund's rule of how in chemistry electrons fill orbital shells with either spin up or spin down. If any of these ring a bell, that is because they are all related to quantum spin of protons and electrons, which is relevant to many scientific fields. If these ideas sound unfamiliar, perhaps this video will shed some light. So what exactly is quantum spin? This will hopefully provide a more in-depth picture and unified understanding of the concept. In quantum chemistry, electrons have two different types of angular momentum. The first type of angular momentum is orbital angular momentum, which is a characterization of how the electrons orbit or occupy the surrounding space of a nucleus which contains the proton. This is very analogous to the classical mechanics scenario of how the Earth in our solar system orbits around the Sun using Kepler's laws, where it takes about 365 days for a full cycle of a year to be completed. In quantum chemistry, there is a second kind of angular momentum which both electrons and protons have, called spin. Spin is a characterization of how protons or electrons seem to be spinning like a top or a dreidel. This is analogous to the classical mechanics scenario of how not only is the Earth orbiting the Sun providing the context of a year-long cycle, but the Earth is also literally rotating like a top at a rate of 24 hours per cycle, which is how we inhabitants of the planet experience day and night. Unfortunately, this classical picture of an electron literally spinning like a dreidel top does not actually make sense, a result that can be shown using classical calculations from electromagnetism. The details of these calculations could be an entire separate video of its own, but to briefly summarize, if we model the electron as a spinning sphere of charge using the Biot-Savart law, the charged sphere can then be broken down into a superposition of concentric spinning disks or rings of charge, and thus we can calculate the total energy throughout all space stored in the electromagnetic fields induced by this configuration. If we incorporate all our confirmed experimentally measured values for the relevant universal constants in this situation, we can show that points on the surface of the electron whose radius we have measured would need to move much faster than the speed of light to induce the experimentally confirmed magnetic field strength energy of Planck constant h bar divided by 2. Thus, if we think only in terms of classical electromagnetism and classical mechanics, obviously this model for electron spin eventually breaks down, and scientists still have a lot of work to do before figuring out the mechanics of what's really going on under the hood with spin. Therefore, due to this mysterious classical contradiction, some physicists in the field of quantum mechanics deemed spin a bit of a misnomer, and instead called this concept intrinsic angular momentum, because this property is intrinsic to all subatomic particles, including protons and electrons, which is of most consideration in the field of chemistry and MRI. Even if not entirely accurate, the spinning dreidel top analogy at least provides a very physically intuitive picture of how to interpret what intrinsic angular momentum actually means in our real and physical world. Just like how the Earth spins about a specific axis, we can represent the spin of an electron with a unit vector depicting the orientation of the axis of supposed rotation and in the direction of the induced magnetic field. This unit vector can be visually shown and geometrically represented in polar form using the Bloch-sphere representation. Notice how it requires two numbers in total, one for each of the two spherical polar angles, to uniquely describe a specific spin orientation on the Bloch-sphere. Now there's a reason why it's called quantum mechanics. Contrary to the continuous angle Bloch-sphere representation of spin, as discovered with the Stern-Gerlach experiment in the 1920s, spin can only be physically measured to be quantized either in the ups or down state. But that's okay, this does not interfere with the overall physical and geometric meaning provided by the Bloch-sphere, as we will soon see, to demonstrate the intuition of how the Bloch-sphere picture is consistent with quantized spin. Let's say our spin is pointing parallel to the plus z direction. That means if we measure spin along the z-axis, we will always measure spin up with 100% probability. Of course, if our spin is pointing directly opposite in the negative z direction, that means if we measure spin along the z-axis, we will always measure spin down. And of course, if our spin is pointing directly perpendicular to the z-axis, meaning it is constrained to the xy plane, then we would of course, following intuition, measure both spin up and spin down with equal probability of 50% since neither is favored. Likewise, by geometric symmetry, if our spin is pointing parallel or antiparallel or perpendicular to the x-axis or to the y-axis, we would get the same resultant measurements, similar to what happened with the z-axis measurements. So this is what the cardinal directions on the Bloch-sphere represent in the context of how spin measurement is quantized. Quick note, it is worth noting that in physics practice, the cardinal direction state vectors of 100% spin up or spin down along a certain direction are actually represented as eigenvectors of the famous Pauli matrices as shown here instead of classic 0-1 vectors, which allows for the mathematical framework of quantum mechanical operators to be consistent with physical phenomena. This idea is not necessary for this video's focus on the overall picture of the Bloch sphere and how MRI works, so I will ignore the details of it moving forward, but it is worth mentioning to explain overall what a projection means coming next. Now, what if our spin is not parallel to any principal axis and pointing in an arbitrary direction? If we pick an axis to measure along, what will the spin be? As shown by this diagram, the probability of spin up will be the projection squared onto the spin up direction along the axis of measurement, and vice versa, the probability of spin down will be the projection squared onto the spin down direction along the axis of measurement. Notice how this isn't a true Cartesian geometric vector projection in Bloch sphere space, but more of a transformation, mapping, or projection of the angle made with respect to the axis of measurement onto the unit circle. That is why it was important to previously mention the Pauli matrices to clarify how this isn't a true Cartesian geometric vector projection in Bloch sphere space. Either way, this mapping scheme still is in agreement with our previous intuition of the directions corresponding to 100% or 50-50 probability orientations. Also notice how by geometry of the mapping to the unit circle of the two projections squared representing the probabilities will always sum up to 1, as expected, since of course not only does the unit circle always have unit radius, but also because probabilities must always sum up to 1. So everything is in agreement. We can keep track of all the possible conditional probabilities in a 3x2 matrix as follows. Quick note, conditional probability or transition probability matrices are quite common in the study of probability theory, stochastic processes, and Markov chains. Here's a claim that I will justify. This 3x2 matrix contains all the necessary information about a particular spin state on the Bloch sphere. In other words, given a unique particular spin state on the Bloch sphere, we have enough information to figure out the corresponding unique particular set of probabilities in the 3x2 matrix, and vice versa. Given a unique particular set of probabilities in the 3x2 matrix, we have enough information to figure out the corresponding unique particular Bloch sphere spin state, and the transformation from one spin representation to another are in fact equivalent one-to-one and onto bijective mappings. Here's the justification. First off, any particular specific unique spin orientation makes a set of 3 unique angles with respect to the x-axis, the y-axis, and the z-axis. Or in other words, no 2 different spin orientations on the Bloch sphere form the same ordered set of 3 angles with respect to the same corresponding fixed cardinal axes. Geometric intuition tells us this must be true, but to more mathematically justify this idea, any particular specific unique unit 3-dimensional vector on the Bloch sphere has a unique set of 3 Cartesian component values by construction. The cosine function is a 1-to-1 and onto bijective function from the domain of 0 to pi or 0 to 180 degrees, and therefore the inverse cosine function, arc cosine function, along the same set of values in its range is also a 1-to-1 and onto bijective function. Therefore, the unique ordered set of the inverse cosine of each of the 3 Cartesian component values will also be a unique ordered set of angles A, B, and C. Now, this unique ordered set of angles A, B, and C undergoes further transformation to map to conditional probabilities of spin up and spin down. What is this mapping scheme again? Here again is the previously mentioned mapping scheme to probabilities from angle with respect to measurement axis. Notice how this is also again a 1-to-1 and onto bijective mapping scheme from 0 to pi, easily seen through geometry of the unit circle. Nesting, chaining, or cascading 1-to-1 and onto bijective mappings preserves the bijective mapping structure. Thus, a unique ordered set of 3 Cartesian components maps to a unique ordered set of 3 angles with respect to the 3 cardinal axes of measurement, which then maps to corresponds to a unique ordered set of 6 conditional probabilities of spin up, spin down, depending on which dimension we measure. Notice again how each row's probabilities will sum up to 1 because the unit circle mapping has unit radius, and also because the total conditional probability of a measurement along one axis will sum to unity. In other words, you will always measure some kind of spin. Therefore, we have shown there is a 1-to-1 and onto bijective mapping from the set of all points on the Bloch sphere to the set of all valid corresponding 3x2 conditional probability matrices, each matrix in the set constructed from its corresponding point on the Bloch sphere, thus justifying the previous claim, which shows the main point of all this reasoning. The same fundamental spatial information from the Bloch sphere is completely represented and preserved in the mapping to the 3x2 matrix of spin conditional probabilities with measurement along each axis. Since any particular unique spin state on the Bloch sphere in spherical polar coordinates can be represented by just 2 numbers of information, which would of course naturally be the spherical polar coordinate angles, That means if we know only 2 elements from different rows, of course, from the 6-element matrix, we can actually uniquely deduce and determine the values of the other 4 elements in the matrix, and therefore any particular valid 6-element conditional probability matrix for our spin system can be uniquely represented with just 2 numbers of information. So not only did we show that there is a one-to-one and onto bijective mapping between the set of all points on the Bloch sphere and the set of all valid spin 3x2 conditional probability matrices, but also we have shown that it takes only 2 distinct numbers of information to uniquely determine the same specific spin state on both the Bloch sphere representation and the 3x2 conditional probability matrix. For the Bloch sphere, those numbers are naturally the 2 spherical polar angles, and for the 3x2 conditional probability matrix, it is any 2 matrix elements that are not in the same row. Now let's check if this conditional probability matrix is consistent with physical intuition, but in order to do so, we have to convert this conditional probability matrix into a joint probability matrix. To do this, we use Bayes' rule of conditional probability, and we multiply each row by 1/3, promoting symmetry between the x, y, and z cardinal dimensions. This way, no particular cardinal dimension is preferred over others for taking measurements, and we can accurately see the overall spin spatial orientation. Nature tends to equally favor the x, y, and z cardinal directions anyway. So this is a joint probability matrix, and let's say if we repeat our probabilistic experiment a multitude of times, if we tally up the total number of each of the 6 outcomes, we get an empirical distribution which can be equivalently viewed as a biased, non-symmetric, 3-dimensional binary random walk, which is of importance in the study of stochastic processes, probability theory, and Brownian motion. From the law of large numbers, our empirical distribution should look just like the joint probability matrix, and additionally that means the average net motion direction of this random walk will also be in the direction of the bias of this random walk. If the bias of the random walk were 0 on average, we would get no motion and end up with 0 on average, since all our steps or motion going different directions cancels out in the end in the total net displacement. To illustrate, if we flip a fair, non-biased coin 1,000 times, we're bound to get about half heads and half tails, demonstrating the canceling out. The probabilistic and statistical justification of this will be discussed more later in Part 2, Quantum Computing and Information. But intuitively, the direction or orientation of this bias in the random walk can indeed be interpreted as the Bloch sphere spin orientation, which is consistent with this joint probability matrix for the 3D random walk. From the probability mapping scheme, the more the spin is oriented towards against a certain cardinal direction on the XYZ axis on the Bloch sphere, the more asymmetrically biased the probability of steps in the random walk becomes towards or against that certain cardinal direction on the XYZ axis, following probabilistic intuition of how the bias or average of this random walk is analogously geometrically and physically equivalent to the Bloch sphere spin orientation vector in the end. To more mathematically show this, we can take our original Cartesian 3-dimensional Bloch sphere unit vector and follow the bijective mapping steps to get to the corresponding joint probability matrix. In doing so, as expected, we get a joint probability matrix that is biased based off of the original Cartesian vector. An unbiased, equiprobable, zero-mean, symmetric random walk would be 1/6 for each of the 6 elements in the matrix, but instead we are perturbed from equilibrium based off of the original Cartesian vector. And in fact, if you look closely, the average net bias in any dimension or direction ends up being just the corresponding Cartesian vector component in that direction or dimension, but divided by 3, and the average overall 3-dimensional direction net bias will be in the direction of that Cartesian vector with same magnitude, but just divided by 3. Therefore, from this reasoning, we have fully justified that both the Bloch sphere and the probability matrix representations of spin states are basically mathematically equivalent and are both consistent with physical intuition and experimental measurement. Therefore, we have bridged and connected the classical view of what spin is to the quantum view of what spin is, and hopefully this provides a universal, clear, and standardized picture of what electron and proton spin are. So very briefly recap, using the mathematical justification in the video, at the end of the day, quantum spin orientation, though quantized to just up or down, can indeed be interpreted as a continuum when there are enough particles present for the probabilistic law of large numbers to hold. This concludes part 1, what is quantum spin?